Adding features to a dataset seems like adding information, but mathematically speaking, it creates a hostile geometric environment. This failure mode is the curse of dimensionality. It occurs as data expands from a few graphable features into thousands or even millions of dimensions. This is a dense 2D scatterplot. As dimensions increase, the hypervolume of the mathematical space increases exponentially. When you extrude this plot into a third dimension, points that were once close together begin to drift. By the time the space abstracts into 100 dimensions, those points shoot away into deep black space. In a million-dimensional space, the area is mostly empty. This is extreme sparsity. Data points are separated by an average distance of over 400 units. To achieve reliable density in a space of this magnitude, you would need more data points than there are atoms in the universe. Human intuition fails in high dimensions. More features do not yield better insights if the resulting space is too vast to measure. The primary casualty of this void is the traditional distance metric, the nearest neighbor calculation that most models rely on. This visualization shows a single central point inside a high-dimensional boundary. Every other data point is pushed to the extreme outer edges, rendering them all roughly equidistant. Distance loses its meaning when every point is essentially as far away as every other point. This empty space forces models to overfit. They draw complex, inaccurate boundaries around the few isolated points, missing the underlying pattern completely. We are left with two problems: a space that is mathematically meaningless to navigate, and a dataset that is too large to store in RAM. To operate in this void, we must first build a mathematical map to find where the data is actually hiding, and then apply engineering to physically compress the space. Real-world data rarely spreads out evenly. It follows the manifold hypothesis, which suggests data exists on a lower dimensional structure. Even in a million-dimensional void, data tends to group together in dense pockets or manifolds. Clustering algorithms like k-means act as the radar used to locate these dense pockets. By identifying these neighborhoods, clustering provides a form of dimensionality reduction. A bright glowing marker now identifies the exact center of each dense pocket. This allows us to replace a 10,000 number coordinate with a single metric, its distance to the cluster centroid. Clustering solves the navigation problem by replacing an infinite void with a finite map of dense, meaningful neighborhoods. Strategy is only half the solution. We still need the brute force engineering required to physically shrink the space. Quantization is the physical mechanism used to combat the curse when handling massive large language models. Specifically, vector quantization uses clustering principles to perform data compression. The process involves forcing high-precision floating point numbers into discrete, lower-precision integer buckets. This reduction in precision drastically shrinks the memory footprint of the vectors. Notice how these scattered data points snap to the nearest fixed intersection points. By rounding numbers to their nearest cluster centroid, we are artificially increasing the data density. Points that were once spread across the void now share the exact same mathematical representation. This reduces infinite continuous combinations into a finite, manageable palette. Quantization bridges the gap between theoretical math and physical hardware. Let's look at product quantization, the specific algorithm used to compress massive LLM embeddings. Here is an array of 1536 floating point numbers. The algorithm slices it into smaller, discrete segments. A clustering algorithm is then run independently on each of those newly created segments. The resulting cluster centroids are stored in a dictionary called a codebook. The heavy block of floats is thrown away and replaced entirely by the lightweight integer ID of the matching codebook centroid. Storing a 32-bit float array is a massive memory burden. Storing 4-bit integers is trivial. When the system needs to read the vector, it looks up the integer IDs in the codebook to rebuild an approximation of the original data. Product quantization restructures the embedding's geometry into a lookup table, converting search operations into simple index retrievals. The curse, the clustering, and the quantization form a sequential pipeline used by modern AI search engines and vector databases. The origin is a massive dataset, for instance 1 billion documents, each requiring a 1536-dimensional embedding. Attempting to store 1 billion unquantized floats requires massive, red glowing server racks that would crash standard hardware. The system analyzes the vectors and locates the dense manifolds within the 1536 dimensional void. It then applies vector quantization, building the codebook from those clusters. The heavy floats are discarded and replaced with lightweight integer pointers. 1 billion documents can now be indexed on a single GPU. This sequence, curse, map, and engine, integrates the geometry, the strategy, and the physical execution into a functional architecture. We started with a million-dimensional void, where computation was mathematically impossible. But because of this quantized pipeline, a system can search through 1 billion documents in milliseconds. This throughput occurs on standard hardware, removing the requirement for infinite RAM. While we trade exact mathematical locations for approximations, the resulting density is what allows the system to function at scale. Conquering infinite space doesn't require more compute. It requires using clustering and quantization to collapse that space into a density manageable by standard hardware.